All right. How's everyone doing today? So, we're going to have the midterm on Friday. Does anybody have any questions about the midterm or anything before I get started? Yes. For the quiz on Friday that you just took? It's probably going to be a little while. So, I just got them. Andrew just got them today, and so probably like within a week or a week and a half. But the goal is, so going into the final, before you take the final, I want everybody to know what their grade is on the first two midterms and the quizzes. So I'll try to get those graded. We'll try to get those graded as soon as possible. Sorry, it just takes a little while because we only have one TA for 200 students. And we do have somebody who's helping grade, but they're a student grader, so they can't do everything. But they'll probably be grading the quizzes so Andrew can focus on the midterm that you take. Yes? Yes, the midterm will be based off of all the homeworks and the discussion and the stuff that we talked about in class and examples that we did in class. Yes. Yes. I'm still working on that, but so far with the midterm, not only have I been given all the constants in the problem, but I even tell you which equation to use, and in some cases put the equation in the problem itself. So even though I didn't post the equation sheet ahead of time because I've been busy, I'm working very hard to make it very clear on the exam so you don't spend a lot of time looking for where the equation is, and you can spend the time solving the problems. Okay? Any more questions about the midterm or anything? Yes? Sorry, what's that? No. Homework 4 is simple harmonic motion, right? You only have to know the fluids for this one. No simple harmonic motion except for pendulum. There might be one question on pendulums on there, or something with a spring oscillating, something basic. But it'll only be worth like 5 points. And I may not even put anything on there, actually. I'm not even 100% sure. It might just be all fluid dynamics, actually. But the simple harmonic motion will be on the exam. It'll be on the final. The final will probably it'll have a lot of simple harmonic motion and a lot of optics and a little bit of review. Probably the final will probably be like 75% new material and only a 25% cumulative. And you won't have to know everything for the cumulative. I'll tell you like which topics that you need to know for the cumulative portion during the final review day. Yes? Yeah, something conceptual. The worked problems that are worth the bulk of the points are going to be on fluid dynamics. Yeah, and based strongly off of the homework and the stuff we did in class. Okay, any more questions? Okay, great. So, let's do some fun demos. Okay, so this one's kind of cool. So, we've got this little like, I forget what they call it, but basically it creates a pressure gradient. So it's not a magnet, but it's something where there's a vacuum here where the air gets sucked out. And so there's a point where there's no air, and what happens is the atmospheric pressure holds it, and so there's a pressure differential, so it sticks and it holds pretty well. Like it can basically support the weight of this. And this is pretty cool. You can try this one out yourself when you come down later on. So this demonstrates like how atmospheric pressure is very significant. And if we had this area being even larger, like a meter cubed, we could have even more, like because of the 101 pascals, 101,000 pascals is the atmospheric pressure. So the air pressure is very significant. You can see it. It's no longer isotropic. This removes the isotropic pressure and makes it so that I can pick this up. It's very cool. Okay, so let's do a demo with Bernoulli's equation. So I've got this. Remember we talked about Bernoulli's equation and how it's actually good for gases? It's actually better oftentimes for gases than fluids. You can use it for fluids sometimes, but the nice thing about Bernoulli's equation is that it works well for fluids that don't have a lot of viscosity. So water is usually okay, but air is even better. So here we have an air tube. This is a vacuum, and it's going to pump air through this tube. And what it is there's two different, hold on, let me turn this down just a little bit. It's feedbacking. There's actually two different tube widths. So the diameter of this tube shrinks. It gets smaller than it is here. Sorry, it still didn't work. Sorry, 1 second. So what we're going to see here, we're going to make a prediction. What do you think is going to happen to the heights of these balls? Is it going to be higher here or lower than the other 2 points where the width is the same? Because remember, Bernoulli's equation tells us how the flow speed and the pressure changes. What happens to the flow speed when we have a smaller diameter pipe? Does the flow speed go up or go down? Okay, and what about the pressure? Okay, so let's see. Let's see what happens here. Let me see if we can make sense of this. Okay. So I've got my... Okay, so these are like the same height here because we have the same diameter. Now, is this one going to be higher or lower? It's lower. Okay, there we go. So you can see right there Bernoulli's equation in effect. So there's less pressure, right? So there's less height there. Even though the velocity is higher, the pressure is less. So we have less pressure in that region. Then the pressure is what forces these up to a certain height. Okay? So that demonstrates Bernoulli's equation. All right, now we're going to do some pretty cool examples. So remember we had the ideal gas equation. P1, V1 equals nRT1. And then you can set, if you have the gas at two different times, if you change the pressure, right, you change the volume of the gas that the gas occupies. You don't change the number of moles, you leave N and R constant. Well, that's precisely what we have in this situation here. We've got a balloon that's got air molecules in it, and it's got N and R, so it's got some amount of air, and the ideal gas constant, R, is constant. But what we can do is, so to start with, this is just at the same, it's actually already, no it's not, it's fine. So it's not at any, it's at the same pressure as our atmospheric pressure, just the glass is a little heavy. Okay, what I'm going to do is I'm going to evacuate the air out of this container so that the pressure will become a lot less. Because what happens is this vacuum is going to suck the air out of this glass container, and then the air, the pressure out here is going to be different than the pressure in there. And so the pressure that this gas is under is going to change. Right now it's under atmospheric pressure because all the air in our room is also in this container. But if I suck out a bunch of the air that's in this container, it's going to essentially be close to a vacuum, and we're going to see what happens to the volume of this gas inside the balloon that changes in response to that. So just to summarize, the pressure here inside here is going to be a lot less than atmospheric pressure because we're going to get rid of some of the gas. So the gas isn't going to be pressing up against this balloon everywhere like it is right now at atmospheric pressure. What do you think is going to happen to the volume of this balloon? Is it going to shrink or expand? Okay, there's going to be less gas pushing on it, right? So let's see what happens. Okay. Okay, does everybody see that? I'm not blowing on the balloon. There's nothing, this balloon is not connected in any way to this device. There's no air entering or leaving the balloon. The air that's leaving is leaving this vessel. So this glass is getting less and less air inside of it. Okay, that's pretty cool. So you can see here, when we change the pressure, we reduce the pressure, we increase the volume. Look at the volume of it. It's a huge difference here. Okay, so then I can sort of unplug that here. Okay, now good luck getting this off here. This is stuck pretty good. Yeah, because there's a pressure difference between here. So this has a pretty big area around it. So there's a significant amount of atmospheric pressure on this. There's almost no pressure inside of here. Most of the gas is gone. The air has been evacuated. So it's like, good luck lifting this off, right? It's not gonna be easy. Okay, and then if I wanna let the air back in, I can change this and I can let air back into the vessel. So air is flowing back up into there now. So the pressure is returning to atmospheric pressure. Gas is filling the vessel, and you can see what's happening as the pressure is going up. The volume is changing and shrinking again. So we'll just give that a few more minutes to go, and as you can see, it's going right back down to where it was before. So this process is a reversible process. This is the kind of reversible thermodynamic situation that we can have, where we can actually make this reversible. Okay. So the next thing we've got is we're going to look at what does the temperature do to something. So we've got these two balloons here that are in this styrofoam. And then what I'm going to do is I'm going to lower the temperature of these balloons by pouring liquid nitrogen over them. So I have to use this special equipment here because we've got a very significant amount of, yeah, you saw that. That was cool. We have a very significant amount of liquid nitrogen that's very cold. And so we're going to lower the temperature. So we're going to look at another aspect of PV equals nRT. We're going to keep N and R constant, but now we're going to change the temperature. We're going to lower T, and we're going to see what happens to the volume. Is the pressure changing? Yes or no? No, pressure's constant because we're at atmospheric pressure. So now we're going to see what happens, though, if I just lower the temperature with some liquid nitrogen. Okay. So actually, they didn't go over. I think I can set this on the table. That'll be okay. Okay. Just going to go very slowly. We definitely do not want this to spill. It's sublimating, so it's going immediately from a liquid to a gas. It's not spending too much time in the, or it's going immediately, yeah, it's like, it's going very fast, changing phase. Okay, so cover this up here. Okay, now let's see what happened to the volume of our balloons here. Oh boy, look at that. And then I remove them from the liquid nitrogen, and look what starts to happen to the gas as it gets back to the temperature that it was before. It starts to inflate again. Almost gets back to like where it was before. Now the material actually gets damaged a little bit by the stress from such a rapid change in volume when it encounters it, but it's pretty close, pretty back up to where it was. And that's actually ice that's formed because there's some water molecules in the air, some moisture, and that just freezes when the liquid nitrogen encounters it. It's pretty cool. And then this one encounters liquid nitrogen again, so it's back to being small again. It's pretty cool. So yeah. Okay, anybody have any questions about this? Okay, pretty cool, huh? It's like looks completely deflated, but it's the same amount of gas. It's there. It's just so much less volume because it's such a lower temperature. This looks really weird, these things floating in this liquid nitrogen. It's such a weird effect. Okay. I think that is good. I think that's pretty much everything that we've got to do as far as the demos are concerned. And then I'm going to be using these pendulums and springs today for the lecture as part of the demo as well. So those will just be crackling a little bit while they continue to freeze because I poured kind of a lot of liquid nitrogen in there. Okay, so we've got our pendulums. Now, the pendulum is an interesting system. I think we talked about this before, that we can use our equations for a pendulum, but we have to use them at small angles. So we don't want to displace this too far, or it doesn't follow a simple pendulum rule for simple harmonic motion. It only acts like a simple harmonic oscillator from like within a small range here. But in this range, the pendulum works. Okay, so now we want to figure out, can we do some calculations with pendulums, and what can we actually calculate by studying them? So let's say we have a clock, and the clock is a grandfather clock designed so that one swing of the pendulum from one side to the other takes 1 second. So it's got a 1 second period, much like this pendulum. In order to do that, what does the length of the pendulum need to be? And what is the maximum speed of the pendulum bob if the pendulum swings to an angle of 8 degrees on either side? So we have this formula for a pendulum. T, the period, has to be equal to 2 pi and then square root of L over G. And we know this, that's 9.8 meters per second squared. So the period of the pendulum is 2 1-second swings. So that's a little tricky. So if you just did this problem, you'd probably put 1 for T, but you actually have to put 2 seconds because it has to swing out and swing back again. So T is 2, and then we have this formula. So we have L. Let me go back to this equation here. Okay, so how do we solve this? So we've got T squared, 2 pi squared, and then I square my square root and just have L over G. Then I want to divide by 2 pi, so I have T squared divided by 2 pi squared times G is equal to L. Okay, so now I have the length of my pendulum in terms of that. So it's going to be T squared over 2 pi squared times G, and then that's just going to be 2 seconds over 2 pi squared. So that's equal to 2 over 2 pi squared times 9.8. So that gives me a pretty large length of almost a meter. And these clocks, they are big. That's why they call them grandfather clocks, because they're pretty good height. You need a pretty large pendulum length to get a period like that. It's all based off of these simple factors of like length based off of that factor of L over G. The square root of that is going to give me my period. Okay, so the maximum speed for this pendulum, so the pendulum's swinging out like this from one point to the next. about some angle of like 8 degrees. And it occurs at the bottom of the arc. So the maximum speed is, of course, here at our equilibrium point, just like a simple harmonic oscillator. So what we can do is we can use this nice little formula for S is R theta. That's an arc length formula. And then R is going to be L, because that's the radius. L is this, R, and then theta is this. And so we have our arc length for that, and then we have to be careful because we have to convert our angle of 8 degrees into radians. So our maximum angle is 8 degrees, and then we have to convert that into radians. So practice this conversion, because you're going to do this conversion a lot for simple harmonic motion. There's 8 degrees, and then we have 2 pi radians in 360 degrees. So our units cancel, and then we're going to have, that's going to be equal to 0.140 radians. And then we have to use that to solve for the distance. So we have A is S maximum is L theta max. So we know what theta max is. So we have L, that's going to be, it was almost a meter, right? Yeah, 0.993 meters. And theta was in radians, 0.140, okay? That's going to give me my distance of 0.139 meters. So that's my arc length. And then V max is going to be omega times the amplitude. So V max is equal to omega times A, and omega is 3.14 radians per second. Now, where did they get that? 3.14 radians per second. Anybody know how we got that for omega? Where did they get that from? Anybody confused? Okay, so what was the period of the oscillation? Remember what we had to have this this full oscillation cycle. It had to take like a certain number of seconds, remember? So it takes 2 seconds to complete a full cycle. But a full cycle is 2 pi, a full oscillation cycle, where the oscillation frequency is like this, in this space. That's 2 pi. So in 1 second, it's going pi radians per second. And that's my angular velocity, omega. So it comes from the fact that it takes 2 seconds for the grandfather clock to swing out 1 period. And a period in radians is 2 pi. So it's pi. That's the omega per radian per second. It's half that. Does that make sense? Everybody see that? Okay, it's a little bit weird, but okay. And then we found the A from before. That's this calculation, the distance. So that's 0.139 meters. Okay? So then we have that the maximum velocity, the linear velocity then, is 437 meters per second. So the velocity, the tangential velocity you could think of as moving, not the angular velocity, like how many angles it's covering per second, but just like the direction it's going this way or that way is given by this. So it's like, okay, this thing is moving. If it's moving this way, at this point, if it's swung through that way, it's going 0.437 meters per second. And then if it swings this way, it's going 0.437 meters per second in either of these cases. Okay? So that's what they're talking about there. Okay? And then we have this pendulum clock with the tick-tock. Each second requires a long pendulum of about 1 meter in length, which is consistent with what you've seen. Okay, so now we have a conceptual question. A person swings on a swing and finds that the period is 3 seconds. A second person of equal mass joins him. With 2 people swinging, the period is what? 6 seconds? Greater than 3 seconds, but not necessarily 6. 3 seconds, less than 3 seconds. Okay, all these different things. Can't tell without knowing the length. Okay, so what do you think? Think about this one for a second. Let's see what we know. The person swings on a swing and finds the period is 3 seconds. Okay, so they know the swing is going to be like a pendulum. And with 2 people swinging, what happens to the period? Well, let's see what we know about a pendulum. Okay, so the period depends on what? It depends on 2 pi square root of L over G. So is there any dependence of mass in this formula? Okay, and there's no, G doesn't change. L doesn't change because the person just jumps on the swing. So from that formula, we would expect the answer to be 3 seconds. Exactly the same. It doesn't change. Okay, yeah. Does not depend on its mass. We didn't change anything else about the pendulum, so yeah. There's no change. Okay. Okay, so this is sort of like from last quarter. So last quarter I did do a midterm, put this stuff on the midterm, but this isn't going to be on your midterm this time. We're doing just fluid dynamics. Okay. So yeah. So let's see. I don't think we need to do any, well, let's see. Do you want to do any midterm review? I think we should probably do some new material. But okay, we'll do this one really quick. Let's do this one. So this is something that could be fair game for your midterm now. Okay, let's do this one as a class. A sphere is completely submerged in water, tethered to the bottom with a string. The tension in the string is 1/3 the weight of the sphere. What is the density of the sphere? Okay, see if you can do this one. This is an Archimedes Principle problem. Let's try this one out. Okay, so how do we solve this one? Okay, so recall this example. We have a free body diagram here. So that's why I wanted to bring this one up, because we have to remember to draw a free body diagram. So we do that free body diagram, and we get the buoyancy force is equal to the weight of the object minus the tension. Okay? So then we can use this example to actually solve for this problem. Okay? So the sphere is completely submerged in water. It's tethered to the bottom with the string. So we can do this density here, and then we have this equation set up like this, and we can solve for it, basically. Okay. So, I don't really think that's... Let's work this one out more precisely. Okay. So the sphere is submerged in water and tethered. The tension in the string is 1/3 the weight of the sphere. Okay. So we've got this. Let's see if we can work this one out. Okay. So the tension in the sphere, the string, is 1/3 the weight of the sphere. Okay, so we've got the sphere, and it's tethered to the bottom, right? It's submerged in water. Okay, what's the density of the sphere? Okay, and then the tension in the string is 1/3 the weight of the sphere. So we have to set this up with a free body diagram. So let's see. Going back to this example here, we've got, it's tethered to the bottom. So it's the opposite of this case. So the free body diagram is not going to look exactly like this. It's going to have a tension that's equal to 1/3 of the weight, right? And then it's got a weight here, okay? And then here's the object. And then what's going up here is the buoyancy force, right? So there's a buoyancy force, there's a tension here, and then there's a weight. So how do we set up this equation then? It's submerged in water, the tension is 1/3 the weight of the sphere. What's the buoyancy force equal to? So the sum of the forces is all in the y direction, and that's going to be equal to the buoyancy force minus the tension in this case, because the tension, it's tethered to the bottom, okay? And then minus the weight of the object. And that's going to be equal to 0. And we know from the problem that the tension is 1/3 of the weight. So we have the buoyancy force minus 1/3 of the weight of the object, because that's the tension, minus the weight of the object is equal to 0. So then the buoyancy force should be equal to, let's see, it's going to be minus 4/3, positive 4/3 weight of the object, right? Because I have to move 1/3, minus 1/3, and 1 over to the other side. So I have 1 plus 1/3. So we have 4/3 weight of the object. That's the buoyancy force. Okay, everybody see that? Okay, now what do? So we have to figure out what is the buoyancy force equal to. So the buoyancy force, so the weight of the object is mass of the object times g. So let's see. So weight of the object is equal to mass of the object times g. And then that's equal to the density of the object times the volume of the object times g. Okay? So then what I can do is I can solve that for the volume of the object in terms of the mass. So the volume of the object is equal to the weight of the object divided by the density of the object times g. Okay? So there we have the volume of the object in terms of these other quantities. And the thing that makes this problem tricky is that we aren't given all of the different things. But the buoyancy force is equal to the density of the fluid. So the buoyancy force is equal to the density of the fluid times the volume of the fluid, right? And then times g. Okay? So what can I do to solve this now? What can I plug in here? So I've got the volume of the object, and then I've got the buoyancy force, and then the weight of the object, right? So I can probably move these things around, right? And I can probably solve for this quantity here. So let's see. So the sphere is submerged in water. So we know what the density of water is. So we know that the density of the fluid is 1,000. And then we have to figure out, okay, I have to move this stuff around. So I have the buoyancy force here, density of the fluid times volume of the fluid times g is equal to 4/3 weight of the object. And then the weight of the object could be related to the volume like that, right? So what do I know and what do I not know? I know the volume of the object is this, but isn't the volume of the fluid displaced the same as the volume of the object? So can I plug this in for that? Right? Maybe? Anybody confused by that? Or does that make sense? Okay, so I plug this in. Maybe I do this. Weight of the object divided by density of the object times g. And then my g's cancel out. And then so I have the ratio of the density of the fluid to the density of the object times weight of the object is equal to 4/3 weight of the object. And then I can just divide by weight of the object, and that cancels. And then I have, sorry if it got a little messy here, but then I have density of the fluid with respect to density of the object is equal to 4/3. And then I have my answer, right? So I had to do a little bit of manipulation there. Does everybody see how I got that? Okay, it makes sense to everybody? A few people are confused. So let's work through this, because the only thing that I was given was the density of the fluid, right? So I had to, yeah. So the buoyancy force equation is that it's the density, the buoyancy force is equal to the density, essentially it's the weight of the fluid displaced. That's the buoyancy force, right? And so what it is in this case, since I yes? I'm not gonna say you would be given all of these equations. You would have to figure out some of this stuff. Like, you'd have to be able to make sense of, like, okay, if I have the buoyancy equation, right, I can express my variables in terms of another variable and plug for it and solve it in there. If I gave you this type of problem, I would probably just give it to you. You'd be given as much information as I was given on this. But that's why I wanted to go over this with everybody, so that it's not like super confusing, right? Because this problem takes a little bit of thinking. Okay, so maybe I should take a step back. Let's start from the beginning and let's summarize what I did in steps. Okay, so I was told, this is all I was told. I have a sphere. It's completely submerged in water and tethered to the bottom with a string. So there's a string holding the sphere. It's tethered to the bottom, and it's floating in the water. Okay. What is the density of the sphere? Okay, so I'm not told anything about the density. I know the density of water. I don't know what the weight of the water is or the weight of the object, but I know how to use a free body diagram. So what I did was I summed the three forces on the sphere. It's got a tension. It's tethered to the bottom, so the tension has to be downwards, right? So I have a minus T. That's this part. Then I have a weight that's also downwards. And then I have a buoyancy force that's upwards. So I sum those forces, and I use the appropriate minus sign for it, and set them equal to 0, because it's static. There's no acceleration. All right, does that part make sense to anybody? Anybody confused about that step? Okay, great. The next thing that I do is I'm told that the tension is like what? 1/3 of the weight of the object. So I rewrite this equation in terms of the weight of the object, because that's fewer variables that I have to solve for then. So I say, okay, the buoyancy force minus 1/3 weight of the object, which is the tension, minus the weight of the object is equal to 0. Then I can create this equation. Because I have the buoyancy force, I move these two over to the other side, and I have the buoyancy force is equal to 4/3 the weight of the object. Okay, does that make sense? How I got to there? Okay, great. Now, what is the buoyancy force? Well, it's going to be the density of the fluid times the volume of the fluid times g. And then that's the volume of the fluid displaced times g, right? But here's the thing. I know that the volume of the fluid displaced is the same as the volume of the object, because the volume of the object is completely submerged. If it was only 1/3 submerged, then it would be like 1/3 that's displaced. But the whole object is displacing that volume of fluid. Does that make sense? That's probably the hardest and most abstract step. Anybody confused about that? Okay, good. So that part makes sense. Okay, and then, so I know that this is going to be volume, so the buoyancy force then is rho F VFG, but it's also rho F VO, volume of the object, times G. Then, this just comes from like basic like, you know, what's the density of the object. So this part's kind of hard too, right? Because I have weight of the object is equal to the mass of the object times G. That's just the weight, right? mg. But what's the mass of the object? It's the density of the object, kilograms per meter cubed, times the volume of the object in meters cubed. That times that gets me mass. That times that is mass, times g is weight. So then I have the volume of the object. I can just move these parts over and divide, and I have the volume of the object is the weight of the object divided by the density of the object times g. So then I have volume of the object in terms of the weight of the object and the density of the object in g, which is great because I actually want to solve for the density of the object. Then, when I plug this in to this expression, don't forget, I have, this is from my free body diagram. So this equation comes from free body diagram. I plug in this buoyancy force here, but I have that it's this, density of the fluid times the volume of the object times g. So then I can rewrite that like this. I have density of the fluid times volume of the object times g is equal to 4/3 the weight of the object. That's just the free body diagram equation. That's where that comes from, again. But then I have the volume of the object is the weight of the object divided by the density of the object times g, which comes from this definition of mass and weight. So I can plug this in for that. So I can move this over, and then I can put this expression in for V naught, weight of the object divided by the density of the object times g. And look, g is on top and bottom, so it cancels out. And weight of the object, so I can just erase that. That cancels out. And then density of the object can just come over to this side. So density of the object comes over to this side. And then I have divide by weight of the object, and that goes away. And that cancels out too. So then the weight of the fluid is 4/3, or the density of the fluid, I should say, is 4/3 the density of the object. So the density of the object is 3/4 the density of the fluid. And we know the density of the fluid. It's just 1,000 kilograms per meter cubed. That's the density of water. So it's going to be the density of the object is going to be 3/4 of 1,000. And that's our answer. Okay? All right, so did that make sense step by step by step? Okay, awesome. So that's an example of like a really interesting problem that we can do with just plugging things in terms of each other. Like using, but you can see why I said study Archimedes' principle. It's a little tricky because you have these little subtleties, right? And algebraic manipulations to do. Okay, great. So I want to give everybody, wish you best of luck with your studies, and I'll see everybody on Friday. We'll have the midterm, and let me know if you have any questions. See everybody then.